All right, section 5.1, we're going to finish today. Addition and subtraction of integers. We're really doing subtraction of integers today. This section divides very nicely into two pieces. And what's wrong, Chesney?
Oh, I just realized I grabbed the wrong thing.
Oh, okay. Thought that I had done something wrong.
No.
Oh, okay.
Sorry.
It's okay. All right. So we're going to talk about a number line perspective for when we left off on last time before we go into the subtraction. And I think it's this one right here, right? 5.3c. Okay. So when we took a look at number lines last time, we had drawn, I'll do this one. And if I have, here's my 0, and if I have negative a, it means I move a, however far that is, in the negative direction, right? And so I'm moving in the negative direction. So this one tells me that I'm going towards the negative. This one tells me from there I continue moving in the more negative direction. That was good English right there. So I've got an additional b units to the left, right? So I moved a units to the left, so this one's negative a now, and I moved b units to the left, that's negative b units. And so what happens here is that this total is a distance of a plus b, but it's negative. And so you see that negative showing up on the outside here because we've moved a units and then we've moved b units, and so we're all the way a plus b units over on the negative side. So I wanted to show a picture for that before we moved on. Now we're on to subtraction. Okay, so integer subtraction. So when we have subtraction, and we've defined it this way before for whole numbers already, when we have a minus b, then the unique integer n, that is the solution, is what happens. So like this is a minus b equals n, when a is equal to b plus n. We had the same definition before. I'll use some numbers to make sense of it in a minute. But we actually had an additional condition to make this work when we had whole numbers. The condition was that a had to be bigger than b. So when we did it for whole numbers, a had to be greater than b. Do you know why? Do you remember why? Yeah, this one's an integer, and before when we did it, it had to be a whole number. So in order for a minus b to be a whole number, a would have to be bigger than b, or it could have actually been equal to. That would have been fine too. But we don't need that consideration now. We don't need that condition now because we can have negative numbers. So we don't have this here when we're working with integers because we could actually have a negative and it would be okay. So the answer, or the idea here, so I'll use something with negatives just to make sense of this. So let's do 5 minus 8. So we would say that 5 minus 8 is equal to negative 3. That is the correct value. But the reason is because 5 is equal to, and we're going to shift some things around. So the b value, which is 8, would move over to the right-hand side. And then there's that n value that's showing up negative 3 to make this work. So this negative 8 would be the 8 moved over to the other side, and 8 minus 3 would be equal to 5. That's the definition of subtraction, okay? Is that there's this sort of missing piece, and it's what would I need to add to a specific piece to get back where I was wanting to go. Okay, so we're going to look at, I think, one more theorem, and then we have the models like we did last time. And most of the models are mirror images to what we did before. That is, they're the same models, but now we're presenting them in terms of subtraction. So our second theorem, or our second definition piece kind of for today, talks about what happens when we're actually talking about subtraction. So I have this very vivid memory of 7th grade math. And I remember this math teacher telling us there's no such thing as subtraction. This is what I remember from 7th grade math. It might be the only thing I remember. Don't remember the teacher's name or anything, but I remember her telling us there's no such thing as subtraction. This is what she was talking about. Subtraction is the addition of a negative number. So she was introducing the idea of negative numbers into what we were working with when she was talking about this. And so we can actually think about or talk about a minus b as being the same thing as a plus negative b, or the other way around if it's helpful to do so. But oftentimes when kids first work with this, it's a very difficult concept to take something like 5 minus 8. Because for how many years did somebody tell them you can't do that? And now you're telling them that they can. It's very frustrating. And so be careful when you're teaching the little ones to not tell them something that's not true. Say things more like, you're not ready to do that yet. Or you'll talk about how to do that later. Because it's very much ingrained in children as they get older that they're not supposed to do something, or they're not allowed to do something, and then all of a sudden they are, and that's very confusing. So this idea here makes it easier for us to think about addition with a negative quantity. And in fact, that actually works much nicer when we're looking at our chip model. And so, you know what, let's start with this example for a chip model, and then I'll show you the example that I have on my paper, because this is a better one probably to start with anyway. So grab out your chips. I gotta change all my tools up here just a second. You're going to take 5 positive chips and put them on your board or whatever, okay? So when we did this before, we had 5 positive chips and it would have looked like this. Okay, so we have 5 positive chips. Does somebody have some chips I can, well, actually, I'll just use the screen. It's good. If you guys have your 5 positive chips, they're gonna match my picture on the screen. Okay, so 5 positive chips. And so when we're talking about adding, or let's start about with the original problem. If you're talking about subtracting 8 like this, what that would mean, sort of in the perspective of what we've done before, is that you're going to take 8 something away, but there aren't 8 things here to take away. Agreed? You do not have 8 objects here to take away. And so if we change the perspective using this theorem into addition, then we would simply add in the negative chips. So we would add in 8 negative chips. Okay. And then we would do what we did last time where we would 0 pair them out. So these are in 0 pairs removed. And we would be left with our 3 negative chips. And our answer would be -3. Okay, so one perspective of this with subtraction, right, 5 minus 8, is actually change it into addition, which looks like the chip model, and it looks like what we did last time. Okay, so it changes it back into something we've done before. Let's actually take the chip model and see what happens, though, when we have other things going on. Now, I know that we have a theorem up at the top of this page. In fact, it's theorem 5.3 part A that tells you negative A is A. So it is a fact, right? You know this is a fact that this is going to become 5 plus 3, which is 8, right? This is a fact. But I'd like to justify for you why a negative times a negative is equal to positive, and a chip model is actually a really good way to do that. Are you ready? Okay, so this says I'm going to start with 5 positive chips. So I'd like for you to start with your 5 positive chips. Problem is, I've got a double negative, and unless I just change it into positives, which is what we're trying to prove we're actually able to do, so don't go doing what you're trying to prove, right? In order to do that, we're going to actually think about this in the language that it's written. This is to remove, and this is 3 negatives. Well, the problem is there aren't 3 negatives in here to remove, and there aren't any negatives at all, correct? There are not 3 negative objects. I need 3 negative objects to be in there for this to work. So in the very same way that we were removing 0 pairs before, we're going to put in 0 pairs. So it is equivalent for us to add in a 0 pair here. This is still the number 5 because this 0 pair adds to 0. I really still have 5 here, it's just expressed differently. And if I can do that once, I can do it twice, and I can do it 3 times. Why do I need to do it 3 times? Because I'm trying to have 3 negatives here to remove. So I can take 3 negatives out now, and I'm left with the answer of having 8 positives. Okay, is that all right? All right, the charge fields model looks the same, but first, yes, Mackenzie?
So, I'm so sorry. I don't know why I'm confused about this.
Okay.
So, we just added in extra positives?
We didn't add an extra positive, we added in 0 pairs. Okay. So simultaneously, we put in positive and negative chips. I'll do one on the outside here so I don't mess up my picture. This right here is equal to the number 0, right? So if I were to put these 2 items, whoops, that's not what I meant to do, I meant to grab that. This is equal to 0. So anytime I either put in or take out 0, it doesn't change values. So what I did is I put in 0 3 times. Now I did it specifically 3 times because I wanted 3 red chips to be able to remove. But in theory, I could, not in theory, but in reality, I could put in as many 0 pairs as I want. I just only wanted really to have 3 negatives, so I only put in 3 pairs. So I insert the 3 negative chips, right? I have three pairs of zeros in so that I could have 3 negatives to then remove. So this removal of the 3 negatives is this part here that's happening at the end. I keep choosing wrong colors. This part here that's happening at the end where I'm removing 3 negatives, that's the removal part right there. So this is what's happening at that point.
I'm sorry.
No, you're fine.
And it's a 0 pair because like the positive and negative like cancel each
Yes, exactly. It's like saying, you know, like I owe you $1 and you owe me $1, so we're really even, right? We don't need to exchange dollar bills. That would be silly. That's the idea, positive and negative from that perspective. Charged field isn't any different. We did this one last time too. The 5 at the beginning means I have 5 positives. And then I need to remove 3 negative charges, right? So this subtraction here means remove. And this one means 3 negatives. There aren't any negatives, so I put in 0 pairs. There's 1 0 pair, 2, and 3. Okay. The value of this circle is still 5. Everything in this circle is still equal to the number 5. It's just expressed differently. And then I'm moving on to the minus the negative 3 part. So the minus negative 3 says I'm going to remove the 3 negatives. And when I do that, I'm left with 8 positives for my total of 8. Okay. The number line on this one is hard to draw. But physically doing this, like, you know, if you drew it on the board and you like move around, works really well. So let me first draw you the number line, which is not going to feel like I've removed or done, it's not going to feel authentic. But there's a way to sort of draw it in it's not great, but it's, you know, the best we can do kind of thing. So we're going to start with our number line. Here's my 0, and I'm supposed to be over here at 5. So here's 5. So I've moved from 0 to 5. I'm going to draw something funny, and then I'll explain it after I do it physically. We're going to draw a circle, and then we're going to move 3 more to the right. Whoops, that's not how I meant to write it. We're going to move 3 more to the right here. This is plus 3, and we end up at 8. Okay, so let me do my desks like I did before, okay? This desk is going to be my 0 desk this time, okay? So I'm at 0 desks. So it says, and I have space for this. Okay, let's make this my 0 desk. I don't think I've got space. So here's my 0 desk. And so I'm going to move 5. So here's 1, 2, 3, 4, and 5. Okay. The negative means I'm going to turn around. And the minus 3 means I'm moving backwards. And I'm over here with Katie where I'm at an 8. The first negative is to turn around, and the second negative is to go backwards. So the best I can do with a picture to show that is that I've done sort of a loop here, right? I've turned around and I'm going backwards now to get to my negative 3. It works really well kinesthetically, and it works not so well at all when you're drawing it, because it really just looks like I did minus negatives positive, which it is. I get that, but the picture part of it is not very intuitive. All right, pattern model. Okay, we did this one before. So we're going to subtract something that we know how to subtract, right? It ends up with positive values. So 5 minus 2 would be 3. And then 5 minus 1 would be 4. Get the number written right. 5 minus 0 would be 5. Because this is whole number subtraction. Remember, the goal is to start with something that we already know how to do. And there's an example in your book that's just really not a good example with patterns of this one. And so when you encounter it, you'll know what I'm talking about. We can discuss it when we get there. There's not a really good way to show it. But this is the idea of patterns, okay? And so what you see happening here is that the numbers are going down 2, 1, 0. So my next value over here should be negative 1, because that's 1 down from 0. And then these numbers are going up 3, 4, 5. So this one would be 6 from the perspective of patterns. Okay? And so we can go another one here, 5 minus, and then this one goes down from negative 1 to negative 2. and the other side goes up from 6 to 7. And then the last one, because it's the one I'm trying to get to, is that it decreases down from -2 to -3, and this one's going up to give us 8. So again, established by patterns, just like we did it by the chip model, the charge field model, moving along my number line, I can see that in order to get from 5 into 3 here like this to 8, it must be that the minus the negative means positive. Once again, justification for why that is a true fact. Okay? All right. Order of operations. My 9th graders hate order of operations. I don't know why. Maybe they don't hate it so much as that they just don't do it consistently, and so it throws them. I'm not sure. Maybe that's what it is. And so what I try to tell my students as well as my children is that we have to have some common language. That's what order of operations does. It gives us a commonness to what we're doing. Otherwise, if you do a problem and I do a problem, we end up with different answers just because we did it in a different order. How are we to know what we were supposed to have done or how we were supposed to have thought about it? We just need a common structure, and this is the common structure that has been developed. There's other ways to describe this, but this is a pretty standard one, so it's the one I usually use. So people usually say PEMDAS, or there's an acronym, P, that people sometimes use with a sentence. Does anybody have a sentence?
Please excuse my dear Aunt Sally.
That's usually the one I hear is, please excuse my dear Aunt Sally. But I've also known of teachers who've let their students come up with very creative ways to remember this, and you come up with things that are different than that. So just so that you're aware, that will sometimes happen. There is something, as you notice the way I've written this, that's a little bit of a nuance. Well, let's just go with this. What does P stand for? Y'all know. This is parentheses. And what this means, by the way, write this next to it because people get confused. It means that anything that's inside the parentheses gets simplified. It doesn't mean that you're clearing the parentheses out all the time. Sometimes that happens and sometimes it doesn't. But it's not about making the parentheses go away. It's about taking what's ever inside of it and simplifying that first if there's a possibility for doing that. Exponents is second. All right, what's M and what's D? Yeah, this is multiplication and division, but I want you to understand that they're occurring on the same line here because their order isn't important. Okay? So I could literally divide before I multiply, and that would be appropriate. So how do we know which one we do if there's not sort of an order between them? Well, it's left to right. So if there's a division that occurs before you get to a multiplication, then you're going to do the division before you multiply. And the reality is that multiplication and division are the same thing. They're exactly the same operation. So if you think about it, you know this to be true. If you were dividing by 2, it's the same as multiplying by the number 1/2, right? That's why. Okay, and so there's not an inherent, like we should multiply before we divide, because they're really the same thing. They're just thought of in a slightly different perspective from one another, okay? And then the A and the S, of course, are addition and subtraction, and it's the same thing. And we've actually explored that now today very clearly, because when we were doing things that said subtraction, where I said minus the -3, or that's not the one I wanted, I did minus, what did I do it with? This one, -8. 5 minus 8, and I said, okay, but we can change that. And we can write this as 5 plus -8, right? Addition and subtraction are exactly the same thing. They're just done from a different perspective, right? And one is adding and negative, okay? So we're wanting to make sure when we look at these that we do them in the order presented. Now, that doesn't mean that you're going to have all of these things present in every problem, right? And in fact, most of the things that you're going to be working with in this section are going to have one item or two of the items, and they're not going to have another one or whatever. They're going to be back and forth a little bit. This example, for instance, doesn't have any parentheses or any exponents, right? Okay, so what does it have that we would do first? Division and multiplication, right? Those two operations are the things that are going to happen first. And the division occurs first simply because it's before it if you're moving from left to right. So I'm going to be very cautious and careful with you on writing down each little bitty step, not because you have to write all of them down necessarily, but because your book likes to ask the question like this. What's the last operation you did before you got to the answer? Well, you got to be a little bit careful. Like, you've got to actually go through it and figure out what was the last thing that I did. By the way, that's actually a really good way to ask a standardized test question too, because especially if a calculator is allowed to be used, right? because most calculators will tolerate you putting that in just fine, and your calculator knows order of operations too. So if you're really wanting to test a student's knowledge of order of operations, it's a good way to ask it. What is the last thing you did? Or likewise, what would be the first step that you would do? That would be a good question as well. So our first step is going to be the 6 divided by 2, which would be 3. Okay, so that is actually step number 1. What would step number 2 be? Yeah, the 3 times the 4. So we would get 5 minus 2 plus 12. And then 5 minus 2 would be my next one, so that would be 3 plus 12. And then I would get 15. So the last step would be 3 plus 12, right? That would be my last step if that was the question, how it was asked. So just pay attention to how much it is you need to get to, how much you need to show to get to what the question is that it's asking. So on this particular one, if you'd done the division and the multiplication in the same step, that would have been fine. There's nothing wrong with that, right? If the question is what did I do in my last step and you happen to do those 2 steps together, that would be okay. But making sure that you recognize that you don't merge those last 2 steps together, right? 5 minus 2 plus 12 is my last step. No, it's not. There's 2 operations there. Which one's going to be your last one? Well, it's going to be the plus 12 one, right? That's going to be our last operation. Any questions? All right.